Anyway, so yeah, I haven't. I just picked this paper because I have forgotten to pick a paper for this day. I just picked one of the ones that I have on my list of future papers. Not that sure what it's about, but let's see. Monitoring large language models activations is an effective way to detect harmful requests before they lead to unsafe outputs. However, traditional safety monitors often require the same amount of compute for every query. This creates a trade-off. Expensive monitors waste resources on easy inputs, while cheap ones risk missing subtle cases. We argue that safety monitors should be flexible cores, should rise only when inputs are difficult to assess or when more compute is available. To achieve this, we introduce truncated polynomial classifiers, a natural extraction of linear probes for dynamic activation monitoring. Okay, it's like something like linear probes, but different. Our key insight is that the polynomials can be trained and evaluated progressively term by term. At this time, one can early stop for lightweight monitoring or use terms from stronger GAL rates when needed. More terms for stronger. Okay. TPCs provide two modes of use. First, as a safety dial by evaluating more terms, developers and regulators can buy stronger guidelines on the same model. Second, as an adaptive cascade, clear cases exit earlier after lower order checks, and higher order guidelines are evaluated only for ambiguous inputs, reducing overall monitoring costs. On two large-scale safety datasets, for 4 models with up to 30 billion parameters, we show that the TPC compete with or perform MLP-based probe baselines of the same size, while being more interpretable than the black box counterparts. And they have code. Okay, so in summary, this is about something like linear probes, but they have more. There's some kind of polynomial, and this is supposed to be in some way interpretable. I guess we will see what's that about later.
What they're trying to say? What are they trying to do? I'm a little confused.
So it seems okay. They have this. Seems the paper gets this truncated. At least waiting for the abstract.
Okay.
This truncated polynomial classifiers,
Mhm.
and I'm understanding from the abstract that is something like a linear probe, like it's some kind of
Ah,
classifier, like it's
okay.
some kind of classifier that is not a linear probe, but it's that kind of thing, where you train it on some data with some
Mhm.
label and on some from some no, you train it on some activations from some label, and you
Okay.
get something from that. I I'm not that yeah, I don't know what the details is, but we can really keep going and see what's that about.
Yeah.
Yeah, feel free to stop me at any point if you don't understand
Yeah.
something to so we can look at
Yeah.
something in more detail or something. Uh I think we can skip the introduction thing. Well, I'll check quickly if it says anything interesting, but usually it's just talking about what interoperability is and whatever. Uh, mm, I'm not sure this kind of thing is that interesting because, well, I'll wait until I actually read it. But, uh, anyway, dynamic activation monitoring return. Probe for interface rotations. Okay, whatever this image is. No, request to some monitors. Okay, here they start talking about the thing. We propose truncated in this paper. They propose truncated polynomial classifiers to achieve these two properties: refining linear precision boundaries by modeling high-order interactions. Specifically, we show how a degree n polynomial can be trained about progressively, yielding n nested submodels. So yeah, I don't know what it means, probably. Once trained, the single tip CPC provides dynamic defense across a range of compute budgets through truncated evaluation. I mean, something I don't know. I'll see what they say later, but when people don't do linear probes normally, part of the reason people do linear probes is because you could do something more complicated. But if you do something more complicated than a linear probe, you are increasingly likely to have the linear probe be making up something that isn't on the model. Like, if you, I don't know, if you want to know if the model is in some point thinking about the concept of, I don't know, dogs or whatever, if it's some image down the model and you want to know if you know so what a dog is. If you have a linear probe and it works, I think that's a nice that's good evidence that the model and that layer is in some sense thinking out the concept of dogs or whatever. If you have linear probes and just from the activations get to if the image has dogs or not. But if you have something more complicated, like you could imagine having a full neural network or something there. At that point, your thing might be the one detecting whether it's a dog or not. So I don't know how much they deal with that or like check how if that's a thing. But I guess we will read further and see that.
So something that, I mean, there's one part of it which is like, I guess, performance, and then there is, I guess, efficiency. But something they mention is interpretability. And even for linear probes, like, I mean, I guess one question is like, for like higher order terms, but like even for linear probes, because these are probes that we are training on, like, I mean, each feature is kind of like some dimension in like an activation subspace. And I'm not sure if that itself is very interpretable. So I'm not sure exactly what notion of interpretability. Like you can interpret any linear model as like, a combination of like individual features. But like if
Yeah.
the individual feature is like a direction in an activation subspace, then I mean, from a human interpretability point of view, is that really interpretable?
I also don't know what they mean by interpretable, but yeah, I haven't gotten to that, to the part where they talk about that. So maybe they have some definition or something. I am confused why this. I'm also confused why this polynomial thing is supposed to be more interpretable than linear probes. Anyway, but yeah. Also, when you're doing probes, you normally don't want interpretability, right? When you're doing probes, you have some idea that you think the model, like some concept that you think the model represents, and you are trying to do a classifier for it, rather than something like sparse encoders when you are just finding a bunch of latents and then you care about where those latents are interpretable or not. And
Yeah, no. I mean, in fact, like the reason why you probe is because there is like an interpretability assumption, the linear representation hypothesis that your concept is linearly representable, and like you assume that, and then you probe,
Yeah, you're
try to
also
train a
assuming
probe.
that the model represents your concept specifically. Like you already has some concept in mind. You are not seeing
Right.
something and trying to interpret it.
Yeah.
So I'm not sure what this whole interpretable, like something like this, like probe, but it has some interpretable parts or whatever. It's supposed to
Yeah.
mean.
Yeah.
But let's. I guess we'll get there in the paper and they'll explain it, and maybe it
Okay.
makes sense or maybe it doesn't. But it does seem to me that you are like even if that's the case, they are solving a different problem that people usually solve with probes. Uh, because when people are using probes, they just want to know if the model, I don't know, has writes malicious code or whatever, or has some representation of refusal or whatever the concept is. Has a linear representation of refusal.
Yeah, and I mean, if I'm getting like the abstract correctly, like I mean, one part of that is interpretability, and the other thing that they at least are trying to emphasize is like cost optimization, right?
Yeah.
That like what they're saying is like, for simpler inputs, yeah, like we should be able to say it fast, like decide faster, and for like more complex inputs, maybe we need like a more complex model. Uh, so
Yeah,
yeah, again, I
that's
think.
maybe nice. But at the same time, like,
Mhm.
I'm not convinced that more complicated models are better in this country.
Yeah, yeah, that's not clear for sure.
They are kind of not subtly overfitting, but there is something like it where your more complicated. Well, but also, I don't know. I guess I will have to see like what they are actually using it for. Yeah. Okay, sorry if I got you there. But yeah. Anyway. Linear representation hypothesis. Okay. They are talking about the linear representation hypothesis here. The prevailing linear representation hypothesis holds that many high-level processes represent as one-dimensional space in a division space. Yeah. However, there is increasing evidence that not all features save it as a simple linear structure. Yeah, there is some papers saying that kind of thing. I'm curious which ones they cite, but anyway. To build robust general-purpose monitors, more powerful alternatives to linear probes are therefore needed. However, unlike existing nonlinear models, EPCs remain statistically instable. Yeah, I don't know what they mean by that. That model integrates higher order polynomials, model multiplicative interactions between LLM neurons. These models how they jointly contribute to the safety configuration. This is based on attribution to specific combination neurons. Yeah, I'm confused by this because isn't this also true of like a, a linear probe? I guess they're comparing to non-linear models. And yeah, you have a linear probe, you can point to which I think that's also what you were saying earlier. If you have a linear probe, you can point to a big linear combination of the input of the neurons. But yeah,
Yeah, no, I think yeah, they're comparing to nonlinear. I mean, in this sense, surely linear models are interpretable. But then if you can't interpret like these individual directions very well, like with due to polysemanticity, then I mean, what does it even mean, right? Like you just saying that, hey, this is deceptive because direction, neuron direction 21 and 23 are combined together. Like, is that really interpretable?
Yeah, I don't think that makes sense. You're right. Sure, it's slightly easier to tell where things come from than it was some non-linear thing, but
Right.
who cares? Nobody's going sparse encoders are linear, and nobody's bothering figuring out which neurons are activating some feature, because in the end, what you care about is which feature activates the current feature, and that's
Right.
some linear combination activating some other linear combination. So I don't know. They might as well have just talked about their thing being better at classifying or whatever, and not bother with this weird interpretability thing.
Yeah, at least till now, it doesn't really make that much sense.
Yeah, I mean, maybe there is some example later and it will make sense, but I'm not suspecting that. Anyway, unless you want to say something else, I'll keep going. Yeah, anyway, progress transparency decisions. Yeah, I don't think it really provides much transparency to decisions. Okay, so they do a bunch of experiments, 2 layers, multiple layers, safety data sets, LP-based probes, and parameter match, while offering built-in feature attribution. Yeah, it's not feature attribution, right? It's neural attribution. That's not very useful. But at the same time, LLMs will find TCP evaluated at a fixed order. Fixed order to bring up to 10% improvement accuracy over linear probes. And up to 6% over MLP baselines. Furthermore, we showed cascaded TPC evaluation yields performance on par with a full polynomial. They require only slightly more net parameters than a linear probe. Conclusions summarized below. Okay. Okay, so they propose the new kind of classifier thing and train them. Two complementary evaluation models of TPC, user-driven evaluation to meet safety badges, and token-driven compute conditional on input ambiguity. We'll see what they mean, but it's probably something like if the input has some middle, not very high but not very low probability of being harmful or whatever, they spend more compute. We show that TPCs compete with or outperform MLP baselines, monitor hardware requests, and true rate sequences. Yeah, if this is true, that's at least something. At the same time, I don't know, anytime a paper says something like this, I suspect some non-trivial chance their baselines are just bad. They just did a bad implementation with the baselines in some way. But yeah. I really have the code soon. Someone could check. Yeah, so this is just late work. Sometimes there's interesting things in the related work that papers haven't seen, but often it's better to just skip it. Often coded features. Yeah, this kind of thing where, for example, here, probing with sparse encoders features. This is the kind of thing that will actually give you interpretable results, right? Because then you will have some features that you can label, and then you will do it, but they are not doing that.
Yeah.
Just another one. Okay, yeah, whatever. Polynomial neural networks. Yeah, okay. Truncated polynomial safety classifier. Yeah, there's a bunch of math notation. I don't think we are going to have time to get into that. It's probably not very interesting. For each input, they have a residual stream. Yeah. Tokens, problem, pooling. Yeah, linear classifier. The probability doesn't will be harmful. Given level examples harmful as a instance of indeed, one can try improve offline using the real-time monitors of problematic requests of model behavior. Yeah, this is just the usual thing where you just train a linear probe on your activations on some harmful text, so it activates on harmful text and not on harmless text, and then you see if it activates in some new test. Only, yeah. Truncated polynomial classifiers. Oh, are you going to say something or?
Oh no.
Anyway, yeah, don't worry. I just thought I heard someone say. So. Anyway, yeah. So far, yeah, this is just a bunch of math to describe a normal linear probe. Truncated polynomial classifiers. Consider a degree n polynomial in the element's activation vector. Using the notation introduced above, we define a truncated polynomial classifier with only its first n. In terms of, yeah, whatever, not going to bother with all that math. The parameters of the degree. Pro. There's a linear thing and these other things with like extra polynomials, I guess. With the where you watch the activation, right? Um, wait, okay. Okay, so yeah, the key thing, I guess, yeah, the important thing is this thing, I guess, that you can train this polynomial classifier and only use, when you finish, only use parts of it. It makes sense. And then you that's the thing where you can spend more or less compute dynamically. You just add more terms to the polynomial.
But how do they decide like how many terms of the polynomial to use at like inference time?
I think they mention this probably later more explain, but
Okay.
here they say in this everything they in the contributions they mention two modes: user-driven evaluation to meet safety budgets, which I guess you have some budget and you just pick the thing, and token-driven compute conditional input ambiguity, which yeah, let's see where they explain. But I'm going to guess it's something like you try with less, and if the probe is unsure, like it outputs 50% or something, you increase until it's sure.
Right. Got it. Okay.
But the probe is pretty late. Progressive training, high. Password with polynomials optimize the full P was located models perform well classifiers. Legal condition. Oh, first let's see this. Okay, so they do some incremental things, so the smaller polynomials work as classifiers. Okay, yeah, so this is trick. So like when you keep adding polynomials, like it still works, and it works increasingly better. They do some trick with the loss for that. I'm not sure I want to. I think I'll look. Maybe if people are interested, we can look more into exactly how it works. But right now, I think I just keep to how they decide, which was the thing we were curious about. Maybe the second more powerful revelation. So input conditional compute. Yeah. Rather than choose a fixed degree for all inputs, we can propagate each input so the increasingly powerful higher order classifier terms only if the certain truncated classifiers in the certain. Yeah, this is the same. They just tried see if the classifier outputs very high confidence on the thing, and if not, they just increase until it does.
So again, like I guess then they also, I mean, they're also assuming that the classifiers are calibrated, that the scores are an indication of probability. Uh,
Yeah, I mean, I guess normally when you train a model, you kind of like there is at least some with it kind of loss functions like cross entropy, whatever that people like if you're using something like cross entropy loss, there is some pressure to the model to be calibrated.
yeah, but almost always like you train a scale-learn model with cross entropy loss, you would like almost like, never get a calibrated classifier. Like maybe, yeah. I mean, you usually have to like if for like a real life deployments, you typically have to actually calibrate them using like post training techniques or something. But I guess
Yeah,
maybe they do that. I mean, yeah. However, you get like some confidence value, I guess.
yeah. I guess maybe they try later how well it works in practice.
Right. Okay. So then they have, okay, if the confidence is low, let's assume that's a reliable confidence, then they just add more terms. And this they do it per token level. So for some tokens, they don't do it, and for some tokens, they do it, which also seems a bit weird.
Only exit literature for deep neural networks and physical purposes. Cascade and miss. Yeah. So at least some of the time this is just a linear probe.
Right. At
And
least
if the
some of it.
linear probe just works and gives confident answer, it's just a linear probe.
Yeah.
I guess maybe, I mean, like, maybe the linear probe does have like false positives where it's very confident when it shouldn't, but maybe the ones where it's unsure. Maybe most of the time increasing the polynomial there actually is worth it.
Yeah, I mean, yeah. Uh, yeah, it's possible, like I guess like in a general sense, yeah, maybe
I
that
don't
works.
know.
Yeah. Yeah, I mean if it's not overfitting, then maybe it is helping. Because that would be the concern that maybe, what if it just overfits, but if the test performance is like so no, another thing they say is like the test, but they compare the parameter, I mean the parameter controlled test performance. So it's not clear to me what that metric means. Like, does it, I think that's something that they were saying, right? That 6% and 10% improvement or something. Where was that?
Experiments.
Yeah, no, across 16 layers in 4 LLMs, we show TPCs compete with or outperform parameter matched MLP baselines. Monitoring for harmful requests. Okay, I guess, okay, this is with MLP. So I guess MLP would always do well unless you control for the parameters, number of parameters somehow. Like unless maybe.
I don't know. I feel like I don't know. This is the kind of paper that is doing some maybe overcomplicated thing that likely in like a year nobody will be using. Maybe not. Maybe it turns out it's actually a good idea. I mean, slightly better than linear probes in some use cases. I don't know. It doesn't seem like super obviously great. But yeah. To be honest, I also picked it because the ones that are more interesting. I was trying to get authors, so I just picked one that was mildly interesting, but not like the one I found most interesting for today because I didn't have time to find the authors or whatever. Yeah, experiments are grouped into 3 sections. Before that, yeah, I do the probability training thing. I mean, the probably seems like it's probably was a lot of work and there's a lot of tricks to get the thing to work nicely. I just not sure this whole adding polynomials thing is even a thing you really want to do. I guess the having different, dynamically spending more compute, if it works in practice, which I don't know, might be a nice feature of the thing.
Yeah. Yeah, as you said, like it really depends on like how well they've implemented because if there is like if you have not been like very careful about like comparison with baseline, like 6% and 10% improvements can really vanish. Like, and I feel like there's like, the baselines that they're comparing with, I mean, they seem fine, but like at least I can think of like other simple baselines too that they could compare against.
Yeah. Oh, someone says, like, kind of says this on the chat. Seems like this approach would work with any kind of cross-cutting classifier because they're training sequentially. Yeah, I guess you could do something like this, but with a different kind of thing with these, these polynomials. maybe there are other ways that work better of getting inspired by this, and someone could make some kind of other kind of classifier where you can spend more compute. Yeah, it can be anything that you can add more filters that spend more compute but are more accurate. Maybe that idea of having some kind of you could also be different kinds of things. Yeah. But I guess at that point it's more like a more general idea. That's not really like the paper is more about this specific implementation. Anyway, let's cascading defense. Yeah, let's look at the experiments a bit, and then we can leave it at that. Unless people want to at anything specific. We train safety monitors on Torr Sky safety datasets. Whatever, base models, different RMs. Yeah, baselines. I guess this problems. Linear probe. Probe. Linear probes. The sample of multiple models that confirm or predict. I remember that some people on the server were like talking about linear probes a lot. Or I don't know what there were some papers. I never got into that, so I don't know. In this sense, yeah, yeah, that's maybe okay. This is the kind of thing that is perfectly possible. They just subtly mess the baselines, and we are not going to right now like read their thing in enough detail to figure that out. I guess this is the kind of thing that you have to wait until to see if people actually use this kind of thing in practice later, and other people try it and see if it works better for their thing. And you can't really trust papers for this. Models 5 times different random scenes. Yeah, maybe pros, maybe it's not even that much percent. Wait. In defense. Production training. Later can go to the conclusion. It was spending on computer when you was ambiguous. Yeah, I guess that's it. If you have something to say, you can say it, or like you can tell me to go to some section and we can look at it. But I think I don't have that much to say about this paper, and it's like it's mostly that. So the summary it proposes this TCP thing, which is kind of a kind of like linear probes. It says some weird things about interpretability that doesn't really make sense. That is supposed to polynomials are interpretable. Which we argued earlier. I don't think it makes sense. And I guess they are better than linear probes, which is okay, maybe depending on whether they mess up the baselines in some way of the experiment. That'd be nice. And lastly, what was the other thing? There is the thing that I think is, you said that is interesting, that this idea of you have some meth classifier that's like a linear probe or something that's low compute, and once you use it, but if it gets an ambiguous answer, you use some more compute intensive method instead. That might be a nice idea. That could work with some other thing if the polynomials turn out to be a bad idea. It does rely on your main, like your model being at least your first being kind of calibrated. And not just be always super confident on the ones that is wrong. But yeah, I guess that's it. Anything else, or do I just leave it here? Yeah, I already see that kind of said that we can call it here, but I'm waiting a bit. Okay, so yeah, well, let's just I'll close the recording on all that and leave it.